Okay. Hello, everyone. Thanks for joining our monthly seminar today. And it's my great honor to introduce our speaker today. Dr. Bibhuti Kumar Jha is a postdoc at Southwest Research Institute in Boulder, where he recently joined Lisa Upton's group and will work on surface flux transport model by incorporating the far side observations of active regions. He got his PhD from Indian Institute of Astrophysics, Bangalore, India, and his thesis is on the long-term study of the sun and its implication to solar dynamo models. Dr. Jha studies solar cycle and its variability. His research interests include the development of automatic algorithm, solar dynamo, and machine learning, etc. He is also interested in public outreach activity, teaching, and photography. Let's welcome our speaker again, and Dr. Bibhuti Kumar Jha. You have your time for your seminar.
Yeah, so thank you, Riju, and thank you for the nice introduction. And let me share my screen. Yes, can you see my screen? I'll make it full. Yeah, okay. So thank you again, and thank you all of you for joining here. So today I'm going to talk about the theoretical model of the near surface shear layer, and it's a relatively slightly different idea that we already have about the near surface shear layer. And I would like to point out here is that this work has been slightly different from the rest of my work in my thesis. So please bear with me. And this is the theoretical work. And so let's start with the large-scale flows in the sun. So when we talk about the large-scale flows in the sun, the first thing that comes in our mind is the solar differential rotation. And we all know that the sun rotates differentially with around 25 days of rotation period near the equator and 35 days of rotation period near the pole. So this has been first discovered by Galileo in the beginning of 17th century. Here you can see the drawing from the Galileo, where it has been shown that, like, it from the GIF or video, you can see that sunspots are moving, and it's Galileo has inferred that the sun is rotating, but it is rotating differentially or not. It has been discovered by Carrington almost around 200 years after that. And today we know that this is the differential rotation profile at the surface based on the various type of observation, and the order of magnitude around 2000 meters per second. So if I talk about the solar differential rotation, there are plenty of observations used from after Carrington. They have used the sunspot and various other magnetic feature that has been seen on the solar surface to measure the solar differential rotation. One of the interesting results came in 70s when using a spectroscopic method, Howard and Harvey had measured the solar differential rotation and noticed that if you measure the rotation rate based on a spectroscopy, you get the slower rotation rate, as you can see here. So the Newton and Nunn has used the sunspot to measure the solar differential rotation, but based on a spectroscopy, you will get the slower rotation rate. And after that, there have been many observations where spectroscopy has been used as a tool to measure the solar differential rotation, and that result has been consistently present. So this leads to the conclusion that the tracers like sunspot gives the faster differential rotation rate than the spectroscopic measurement. So it tells that there is something very interesting happening near the surface. So then Rhodes in 1990 came up with the idea that if you use some tracers to measure the solar differential rotation, it is actually giving you the rotation rate of their anchored depth. So if you use the sunspot, you are actually getting the rotation rate at the anchored depth of the sunspots. Now, we also know that the different sizes of the sunspot have the different anchored depth. If that is the case, and it also anchored depth also depend on the life, like in which phase of their life the sunspot are. So that is our current understanding. If that is the case, what we can expect is that different classes or different sizes of sunspot will give the different rotation rate. And that is indeed the case. which was first discovered by Howard. So if you use that, the different sizes of the sunspot to measure the solar differential rotation, you will get the difference rotation rate. A similar result has also been seen from the Kodaikanal Solar Observatory data in one of my work, where I have noticed that, like measured that if you use the bigger sunspots to measure the solar differential rotation, you will get the slower rotation rate. That indicate that indeed the case that the rotation rate depend on the anchor depth. So when you use the different feature, you will get the different rotation rate because of their anchor depth, and they are in the different phase of their life. So this asks the question, what is happening just below the solar surface? And a great breakthrough came when after the helioseismology. So this is the plot from the helioseismology, where helioseismology has mapped the difference rotation rate of the sun in the solar convection zone and even below that. And you can see here, there is very interesting thing happening very close to the surface. So the sharp change in solar differential rotation that we see in this contour is near the visible surface is termed as the near surface shear layer. Now, the first attempt to explain this NSSL came in 70s, even before the helioseismology has measured the rotation rate inside the sun. So this idea was actually based on the constancy of specific angular momentum by Foucault and Gilman. So what they have mentioned is that, like, as we reach to the surface, the convection is such a way that it try to mix everything and you get the constant specific angular momentum. If that is the case, then what we expect is that like rotation rate will decrease with the radius, and that can give rise to the NSSL. But helioseismological observations has shown that there is no such constancy of specific angular momentum in the observation. So that cannot be the possible answer for the NSSL. Here I would like to remind you that if you have any questions in between my talk, please free to ask. Unmute yourself and ask. Okay, so that specific constancy of a specific angular momentum could not be the answer for the observed NSSL. Then in the recent years, there has been plenty of work to explain the NSSL, and the important works were from Guerrero et al. In 2013, and then Hota et al. In 2015, and then Metelsky in 2019. All of them have attempted to explain the NSSL based on the numerical simulation of their solar convection zone. Particularly the Hota et al. And Guerrero et al. Had shown that actually the Reynolds stress plays an important role in the creating NSSL. And then Metelsky et al. Has suggested that the steep decrease in the top layer of the solar convection zone is actually responsible for the NSSL in the sun. So the widely accepted view is that the Reynolds stress become very important as we reach close to the surface, and that leads to the violation of the thermal wind balance equation that I will be going to talk about later in my talk, what is thermal wind balance equation. But and there's another work by Chaudhary in 2021, and based on the order of magnitude calculation, we have shown that there is an alternative explanation for the NSSL without the role of Reynolds stress, and actually the thermal wind balance equation is valid, and that can itself give rise to the NSSL. So that is the idea behind this talk today. So I'll be going to discuss about how the thermal wind balance equation can give rise to the NSSL. So let's start with what is thermal wind balance equation. So if we look at the fundamental equation of meridional flow, and for the derivation, you can look at the Chaudhary 2021A, a good review paper on the meridional circulation. So this is the pi component of omega. So if you look at this equation, the first term that we call a centrifugal term, second term that we call thermal wind term, and the final third term is called the dissipation term. Now, in this equation, if meridional circulation is maintained in a steady state and the dissipation term is negligible, which has been shown again in Chaudhary, that the 4 order of magnitude dissipation term is 4 order of magnitude less than the centrifugal term. So that means if that is the case, we can ignore the dissipation term, and then we will get the centrifugal term will be equal to thermal wind term, and which is this. And this equation is called the thermal wind balance equation. I'll be using this equation throughout my talk again and again, and it will play the central part of our theory of near surface shear layer. So this is the point where we differ from the others. So most of them will believe that at the top of the layer, top of the convection zone, this thermal wind balance equation is not valid because of the third term, that is dissipation term. We cannot ignore that dissipation term in the top of the convection zone, and that means that this centrifugal term that is arising due to the solar differential rotation cannot be balanced by the thermal wind term, and we need dissipation term to balance this, and that actually gives rise to the NSSL. But here we come up with the different idea that the thermal wind balance equation is still valid in the top of the solar convection zone, and it can give rise to the NSSL that we observe in the helioseismic observation.
I got a question.
Yeah.
What's the coordinate Z?
I didn't get you.
The coordinate Z?
Yeah, I will come to that. By in the in the next coming plot, I will show. It is actually the direction parallel to the rotation axis.
Okay.
So now let's try to understand what is the physical interpretation of this thermal wind balance equation before I go into the detail how it can give rise to the NSSL. So, but before that, let me slightly simplify this equation so that we can better understand this equation. So if we assume that the ideal gas case, we can write entropy, specific entropy, something like this. And then let's assume how we write the temperature. So this direction is the direction of Z, that is parallel to the axis of rotation, G direction. So now let's talk about what will happen to the convective cells when it is moving along the rotation axis and when it is moving perpendicular to the rotation axis. That means one plasma blobs or convective cells that is moving along the rotation axis will experience no Coriolis force, but one that is moving along the equator will experience the maximum Coriolis force. If that is the case, what we can expect is that the temperature will be efficiently, like heat will be efficiently transferred along the rotation axis, and it will not be that efficient because of the Coriolis force when it moves along the equator. So what it will introduce is that the temperature of the sun will depend on the latitude. So it will introduce the latitudinal dependency in the temperature. So if that is the case, what we can write is that, and it has been also shown by Matelsky et al. In 2020, but there they have not discussed the physical interpretation of that temperature difference. So what we can do is that we can split this temperature profile of the sun, TR theta, in the two terms, the temperature at the pole plus some delta TR theta, which depend on R and theta as we move from pole to the equator. And now if you use this T in this equation, we will get delta S by del theta by something like this. And if we substitute this in our thermal wind balance equation, we will get something like that. Again, I would like to point the centrifugal term. This is called the centrifugal term, and this is called the thermal wind term. So let's try to understand this term. So we know that the solar differential rotation depend on the latitude. So as we move higher in the latitude, the omega is decreasing. So if you take this direction, a line that is the direction of Z, the omega here will be higher and omega here will be lower. So what will happen is that the centrifugal force at this point will be higher than this one. So now if you subtract some mean value that is calculated along this line, you will get the resultant force in this two direction. And that it will try to move the plasma from equator to the pole. And that is actually the observed direction of meridional circulation. Now, as I mentioned, if the pole is slightly hotter, as the heat transfer is more efficient in the direction of rotation axis, so we expect the pole is slightly hotter. If that is the case, we can say that the thermal wind term try to move the plasma from pole to the equator. Now the question is that, like, is it possible that the only centrifugal term, and we will get the like same temperature everywhere, delta T is 0, and only the centrifugal term can drive the meridional circulation? The order of magnitude calculation has shown that this cannot be the case, because centrifugal term can drive the meridional circulation more stronger than what we observe. So only centrifugal term cannot be responsible for the meridional circulation. Another idea is that since the centrifugal term, this term, we all know that this will also move the angular momentum, transport the angular momentum to the pole. And if that is the case, it will, after some time, you will see that that will change the omega, and ultimately you will see the decrease in centrifugal term. So that means these two terms together is responsible for the meridional circulation that we observe. And ultimately, this is the centrifugal term that is slightly higher than the thermal wind term, and actually responsible for the meridional circulation that we observe in the sun. So let's talk about now how this thermal wind balance equation can give rise to the NSSL. So to understand that, let's look at this image where we see that the point, like we know that from starting from around 0.7, we have a convective zone. So now in the convective zone, at the top of the convective zone, based on the observation of the granules, we have seen that the convective cells are very small, but the simulation has shown that the size of convective cells are actually very large as we go deeper in the convection zone. Now, if that is the case, the turnover time for these big convective cells will be higher, and that means that will be comparable to the solar rotation period. And that is the case, then the centrifugal term will try to affect these. But as we reach to the point higher in that solar convection zone, the cells are very small, and the turnover time is very, very less than the solar rotation period. So what we can expect is that the Coriolis force will not have much effect on these convective cells. So if that is the case, then what will happen is that as we move from bottom of the convection zone, there will find some place where this Coriolis force, although we know that this will happen very gradually, but for simplicity, let's assume that at R equal to RC, this transition is happening. So what we can say that before, for R less than RC, we can expect the Coriolis force to affect the convection, but R greater than RC, the convection is not affected by the Coriolis force. So another way of saying that is that the Rossby number is very high in this layer, and there is no effect of rotation in this. And the effect of rotation is very high in this region, and the latitudinal dependency that we talked about, that will be there in the deeper convection zone. But at the top of convection zone, the latitudinal we cannot expect the latitudinal dependency. But the latitudinal dependency that we see at R equal to RC, that will continue to the surface. So whatever latitudinal dependency you see at R equal to RC will be same in the region where R is greater than RC. So mathematically, we can say that there is no effect of Coriolis force on the convective cells in R greater than RC. So if that is the case, we can write dt by dr becomes independent of the latitude in this region where R is greater than RC. So we can write something like this, and then ultimately we'll get delta T for R greater than RC will be exactly same whatever it is at RC. So for a given theta, if delta T, we get the delta T at R equal to RC, that will be mapped to the surface. So that is our idea now. So what it means is that in this equation, this term in the bracket del y del theta del T will remain constant in the region where R is greater than RC. But in addition to that, the temperature is falling very sharply in this region, as you can see from the temperature profile of the sun. So what it do is that so this term will grow. And if this term is growing, so the basic idea is that this is actually balanced by the dissipation term that we have neglected earlier. That is the widely accepted idea, and that gives rise to the NSSL. But we say that the order of magnitude calculation, based on order of magnitude calculation, the rise in this term cannot be balanced by the dissipative term alone. And the centrifugal term has to rise to compensate the effect of the rise in the thermal wind term. And that has been used in Chaudhary et al. In the order of magnitude calculation, and he has estimated that the pole equator temperature difference based on that, if that is the thermal, using the thermal wind balance equation. So this work is particularly like the work that has been done in 2021B, where they have Chaudhary et al. Chaudhary has used the order of magnitude calculation to estimate all this. So we have substantiated that idea, and we have studied in more detail how this thermal wind balance equation can give rise to the NSSL. So how will we proceed?
Excuse me,
Yeah.
may I ask a question about
Sure.
previous slide?
Yeah.
I'm a little bit confused because according to second bullet, you assume what no temperature gradient for different latitudes, right? But in last bullet, you are saying pole equator temperature difference.
Yes, so
it seems for me kind of contradiction. Can you explain it a little bit more?
yeah, so what we are saying here is that dt by dr become independent of latitude. So in the region where r is greater than rc. So in this region, what we say that whatever latitudinal dependency you will get at r equal to rc, that will remain same. So although in this region, temperature of the sun is falling very sharply, but the rate of change will not fall, will remain same. So dt by dr will not depend on the latitude, but it is still falling. But whatever dt by dr you will get at like any theta, it will remain same for all theta.
But delta t itself will still depend on theta, and that's why you still get the derivative in the term.
Yes.
Yeah. Okay, thank you.
So how will we proceed? So what we'll do is that first we assume some RC value, and then what we'll do is that we solve this equation for that RC value and calculate the omega. For given omega, we calculate the delta T in this region where R is less than RC. And then whatever delta T we will get at R equal to RC, we use that delta T and again solve this thermal wind balance equation for omega. So that is idea, and we'll try to compare our omega with the existing observation to demonstrate are we able to produce the observed omega or not in the top of the solar convection zone. So here again, I would like to point out that for the T, we have used the model from the Christian and Dalsgaard 1996 model for the solar like temperature profile. And we assume that that profile has, this is the profile that we see along the rotation axis. That means it is not, there is no effect of convection in that. So based on this profile, we use the T. So now our methodology in the nutshell, we'll start with RC, and then we solve the equation for delta T for a given omega r theta, and then we will use that delta T at R equal to RC to solve the thermal wind balance equation. So now it's time to talk about the observation of omega r theta. So this is the observation from omega r theta from the helioseismology, and we can see that the signature of NSSL, and we are expecting that RC will be coming close to this point. So one can argue that since in our input data, there is already a signature of NSSL, and that is giving rise to you as a NSSL in the final result. So what we have done is that we have used some analytical, or we can say the empirical relation taken from the Sochu and Servanov et al. In 1999, where there is no signature of NSSL. And it has been shown that this is the like good fit from this data, but there is no signature of NSSL. So we have used this data as our first point, and then we first calculated the delta T based on this analytical expression. And we can see here that how this delta T is varying. So you can see as we go from the 0.7 to around 0.98, we can see that delta T is increasing. Delta T is decreasing. So at the bottom of the convection zone near 0.7, we have large difference in the temperature from pole to equator. As we move towards the surface, this temperature difference is decreasing. And if we look at the profile for delta T for different RC value, and you see there is something interesting here, like we would like to point out here, that as we move from 0.7 to 9, you can see it is continuously coming down. I will come to that again in the later part when I will be using the helioseismology data. So because this there is no overlap, it's falling in the order. So all 0.75 to bottom one, they all are in order. So let's talk about what we'll get. What we have done, that we have used the different RC value and look for the NSL. And we can, this dotted line represent the value of RC. So we can see here that the RC value that you can for 0.92 in all these 6 cases, we get a signature of NSL, which was not present in the data itself. So that means this NSSL is coming out of our model. It is not the artifact from the, or it is not getting translated. I will not say artifact. It is not getting translated from the original omega r theta. Along with that, what we have done is that, although our input data does not have any signature of NSSL, our model is able to produce NSSL-like feature in the omega. So then we also look at the pole equator temperature difference, and we can see that from 0.75 to as we reach to the surface, it is monotonically falling. Although because this is not the real observation, it doesn't have much physical meaning right now, but it is expected based on the profile of the omega, because that is completely radial in the top of the convection zone. Now it's time to talk about use the helioseismology data. So if you do that, the delta T profile is now not that simple. So earlier we have seen that all the contours were falling very sharply to the equator, but it is not like that. And here, if I plot again the theta, but one thing that I point out here is that because the helioseismology data is not that reliable in the near the pole, so we have restricted ourselves from 20 degrees. So if you plot this delta T for different RC, now you can see. So 0.93, 94, and 95, they are in order, but then there is a switch here. So 96 is coming down and 97. So there is something interesting happening here. And that can be also seen in this plot, this yellow region, where the temperature difference is almost 0. And that has been pointed out by the Sochu et al. So these are called a submerged polar jet. And we say that this submerged polar jet is responsible for this effect. Since that is not our ultimate goal, we have not get into detail of why there is submerged polar jet, but it has been well seen in different type of the helioseismological data, different type of inversion. So this is consistently present in all type of the helioseismological observations, but we'll not go into the detail here. Then let's talk about the NSSL based on the observation. And again, we have done the similar thing. For different value of RC, we have plotted the NSSL. So what we have done, again, I would like to point out here that we have calculated the delta T at this dotted line, and we use that delta T to calculate the omega in the top of layer. And here we have compared it with the observation. So the red dashed line is from the observation, and this black line is from our model. So you can see for RC equal to 0.95 solar radii, 96 and 97. So they are in good agreement with the observation. But for 0.98, there are very thin region where we can see that so it's very difficult to say, and we are expecting the NSSL near these regions. So these are the possible candidate for RC. But based on the visual estimation, it looks like RC is the best answer for the, that is in best matching with the observed omega. So to further verify that, what we have done is that we calculated the RMS error at all grid points in this region where R is greater than RC, and we have indeed seen that point R6 gives the lower value of, and see the difference is not too big, but still 0.96 gives the around error of 1.3%. So we can say that RC equal to 0.96 gives the best estimation of the observed NSSL. And then for this value of RC, we have also calculated the percentile error at each grid point, as you can see, and see that the error is most of time less than 5%, which is important because the helioseismology data itself has around 5% of error. So it is important to have an error less than 5%. But as you go to near the surface, you see the error is large. So the possible reason is that the thermal wind balance equation breakdowns as we go very close to the surface, and actually the dissipation term that is playing very important role there, and it cannot be ignored there. And that is the region these errors are, we see this difference. Now it's time to talk about the observation. So is it possible to do the pole equator temperature difference that we estimate from this work? So in this case, in case of the observed omega, this pole equator temperature difference is still falling monotonically up to 0.925. And this is the region where we have seen the submerged polar jet. So after that, again, it is picking up. So what we have done is that we have compared with the observation. So there is a work by Rast et al. In 2008 using the PSPT Mauna Loa Solar Observatory data. And they have studied the latitudinal variation of the photospheric intensity. And based on their study, they estimated that the PETD is around 2.5 Kelvin. Here, I would like to point out that the temperature difference is only 2.5 Kelvin and the pole is 2.5 Kelvin hotter than the equator, the corresponding brightness will be only 0.16%, and which is very, very difficult to measure. So apart from the instrumental effect, the presence of polar faculae make these measurements very difficult. However, Rast et al. Has claimed that their measurement of enhanced intensity near the polar region is a real physical effect. It is not the artifact or not the effect of other bright feature that is seen near the pole. So when we compare that, we have noticed that for RC equal to 0.96, actually the PETD is around 2.5 Kelvin. But again, I would like to bring into your notice that our assumption that we have assumed the sharp transition of the Rossby number at RC equal to 0.96 of our RC, but it is expected to be very gradual. So while comparing this with the observation, we have to keep that in our mind. So that will brings me to the final part of my talk. So that is based on thermal wind balance equation, we have given the theoretical model of the NSSL, and our model is able to produce the feature like NSSL, even using the analytical expression of omega r theta, where we have not seen any signature of NSSL in the input data. And then we have used the helioseismic data, and we saw that our model is successfully able to produce the observed NSSL for RC equal to 0.96 R0. And the pole equator temperature difference also saw the good agreement with the observation, but a careful measurement of pole equator temperature difference in the near future would enable us to access the value of RC. So it will be hoping that in the future we'll have the better instrument and better technique to measure the value of pole equator temperature difference, and then we'll be able to compare the delta T profile as well. So based on our model. And then finally, for the simulation, so simulation may also eventually be able to estimate the value of RC. So ultimately, at the end, I will say that if we can somehow map the latitudinal dependency of solar temperature at the surface, we can estimate the RC, because the same at whatever delta T profile we get at RC is mapped to the surface based on our idea. So this work has been published in 2021. So if you are interested more about the work, you can go to this reference. And thank you for your attention. And now I will be happy to answer your questions.
I have a question. But
Yeah.
thanks, Bibhuti. That was great. I feel like
Thank
I
you.
actually understand a little bit more about the near surface layer than I did going into this. So, but in terms of matching your model to the helioseismology observations, I agree. It looks really, really good, except near the equator.
Yes.
And maybe you talked about this, and I just in processing all the information missed it. But can you explain why there's that discrepancy towards the equator, where presumably the helioseismology information is more reliable, and if there's, is there another R crit that matches better at the equator, but maybe not so well at the higher latitudes, or something along those lines?
Yeah. So in the mid latitude, even in the higher latitude, if you go, you see the discrepancy and small discrepancy. But here, what weaken is that is due to some that submerged polar jet that we have mentioned. And that is actually playing some, because we don't have proper understanding of what it is actually, what is causing that. So we say that that could be the possible reason for this, but we are not sure about like why we see the difference, because, and also like maybe we can tune RC for even more, like we have tried 9.5, 9.6 and N7, and we have not tested, because our idea was not to exactly match with the observation. Our idea is able to produce the observed NSSL or not. So
I think Irina had a question next. Irina?
Yeah, thank you very much for very interesting presentation. My question is about your matching with observations published by Rust in 2008. And my concern is you are comparing layer at 0.96 solar radius, but in paper they actually analyze continuum intensity or something like this. So it really, you know, very large distance between your location and observations, but also in observations we can have brighter polar region just because of facula, for example, or other physical reasons. So, and I'm not sure why you are so interested to reproduce such results on depths like few degrees below, a few percent below the solar surface.
Yeah, so like if that delta T, like that is around 2.5 Kelvin that we have estimated. So if that is the case, that we know that that is very small, and apart from the instrumental effect, and it's very difficult to measure that. So like we were looking for some observational evidence that is bad, and we found, like, based on our knowledge, there is only one work by Rust et al. And they have estimated that pole equator temperature difference based on the intensity variation, as you have correctly pointed out. Like this brightness could be due to the other bright features like faculae in the polar regions, but they claimed that. So we have not done that thing, but they claimed that like their method is such a way that they have get rid of those effects, and the difference that they are getting in the brightness is the physical, not because of the other features in the present in the solar surface, and particularly near the poles.
Yeah. Okay. I don't know if I may ask another question. Is it okay? I'm wondering if your model able to do predictions, say if we discuss about this particular slide, what we see right now, you excluded for some reason polar regions, but is it possible for you to give kind of prediction what we expect to see if, say, we will have perfect observations?
Yes, so because why we have restricted ourselves is because of the helios, because we are using the helioseismic data, and that to calculate delta T, and that helioseismic data itself has some uncertainty as we reach towards the pole. So we don't want to include that, because that will be included in our model.
Okay.
So that is the reason. So in the future, if we have the better helioseismic measurement, definitely we look into that.
All right.
Yeah.
Next was P. Rajaguru.
Hi.
Hi.
Hi. Thanks for an interesting talk.
Thank you.
I have a question on your plot, which shows the temperature difference determined from helioseismology. I think you refer to a submerged polar jet. Okay, maybe this plot.
Yes, this plot.
So I'm just wondering what the implications of the smallest temperature difference at that particular depth, around 0.92 or 0.93.
So like we still don't know what submerged polar jets are, and like in the map we have seen that if you look at the delta T map for this particular case, so yes, so, and even the helioseismology map, so this map, if we go to this map, what we are expecting is that the delta omega squared by delta Z is negative in the convection zone. But if we go into this region, what we see that it's sometime at some point in the near mid latitude, it is 0, and even it is positive at higher latitude. And that is very interesting, but we don't know the region right now because I think I don't know about the helioseismology much, and but we don't have the proper answer for that, and that is leading. And because we don't know what is polar submerged jets.
Yeah, this polar submerged jet is it the one from SCO 98? That same one?
Yeah, so
Yes,
that's one.
yes.
Yeah.
Yeah, but I think that's usually thought not to be real. I mean, that's there
maybe
is
like,
no submerged polar jet. That's
yeah. So
I
then
can
one like
that is our
maybe.
consensus.
Okay, so we can try with the different helioseismology data and see what will be the effect of that instead of using this data.
Right. So the point of my question was that in your equation, if it indeed is the case, the centrifugal force will dominate at this location, right? Because the temperature difference is the minimum there. So the thermal wind term is much less than the centrifugal term, isn't it?
Yes, yes.
So in that situation, then you will drive a meridional flow at that depth.
No, but
towards the pole.
again, your delta omega is also decreasing. Delta omega is squared by delta Z at this point. So it's not only the thermal wind term. So because what you are seeing this delta T is smaller because of the other way. So because your delta omega squared delta Z is decreasing, that's why you see the difference delta T is small. It's not in our model, because we have calculated in this region, we have calculated delta T using the omega. So,
all right, thank you.
Yeah.
Okay, Sushant Mahajan was next.
Sushant, we can't hear you.
I think he muted because of the thing. He's adjusting some
now?
sound. Yes.
Okay. Very nice talk with Bibhuti. I just wanted to ask you, how much of an effect could the addition of turbulent stresses have on this result?
So like in our model, so we say that the turbulent stress will have large effect as we go close to the surface, not in the region that way in our domain. So like around maybe after 0.98 or 985 or 99. But we believe that there will be not much effect of Reynolds stress because our order of magnitude, our calculation has shown that like it is 4 order of magnitude less compared to the centrifugal term and that like thermal wind term as well.
All right, thank you.
Yeah, but at the end, like we have seen that if you look at this plot, we have a large error, like around 5% near the surface. So in this region, we can say that maybe that stress will play a very important role and it cannot be ignored.
Makes sense. Thanks.
Okay, Nick Featherstone in the chat said this was a very interesting talk. Thank you. I need to run to another appointment, but we should chat about this at SWERI sometime. So definitely check back with Nick if you see him wandering around the halls. Are there any other questions in the audience?
Yeah, where'd you who brought this submerged polar jet to your attention?
So actually, like this is the we have spent a lot of time to look at this particular dip.
Oof. Oh, that dip. Okay.
Yes. So like when we have seen this particular plot, if you go back to this particular plot, it's monotonically decreasing that we were expecting.
Mm-hmm.
So we haven't. But when we looked at this plot and this dip brings the note, bring us to look for what is the possible region for that. And it can only be possible that if delta omega squared by delta, there is something happening with that term there. And when we carefully looked at it, and this is also present in this plot, if you see, the contours are going down and then again coming up. in this region where delta T is almost like 0. So what is the reason for that? So delta T is 0 only possible that like if there is no delta omega square term is also approaching to 0.
Hmm.
And that like thing we looked at, and then like we came to that this could be the possible region, but yes. And like we have looked at some literature and found that it is consistently present in all the observation, and that's why we believe that it is the real feature, not the artifact of the method or something like that, other effect. So
That's okay. That's not SCO's opinion.
yes. So
But actually, that jet though is not present in all. I mean, if you look at the, well, anyway, we can talk about it more later. But I'm extremely interested to see you refer to it at all, because until this very moment, I thought it was universally acknowledged as an artifact. So yeah, let's talk more. It'd be amazing if it turns out it's been real this whole time.
All right, Irina, you're up next.
Yeah, my question is if submerged polar jet is real, do you see evolution of the jet in time?
I didn't get you the last term that you have mentioned.
My question is, do you see any time evolution of this jet, properties of this jet? So when if it getting stronger, weaker, or maybe disappear sometimes, something like this.
So like, I don't have much idea about that right now. So how it will affect it.
Yeah, its dependence on the B angle is what is one of the things that makes us think that
Sorry,
it's not real.
sorry, okay.
That's a good question, though. It'd be interesting to know. All right. Any other questions?
I'd like to ask a question. I can't figure out how to raise my hand, unfortunately.
Go for it, Dave.
A key observation about the surface shear layer is that the logarithmic gradient of the angular rotation rate does not match what you get from conservation of angular momentum, which is, of course, led to studies like this on, well, since that's not the answer, what is it? You've brought up a very viable possibility here, but Reynolds stresses and Maxwell stresses are still there. So I think ultimately the answer is far more complicated. Also, there's a meridional flow involved. So a thermal wind assumes that instead of getting a meridional flow, you balance the vertical gradient in rotation rate by that latitudinal force so that you don't force a meridional flow. So I think this is a good it's a good introduction to another possible component of it, but I have little doubt that the ultimate answer is far more complicated.
Yeah, but yeah, I know that there is a like in the it's widely believed that the Reynolds stress play a very important role, and actually that was the reason we have a struggle like around for 6 months with the referee on this one. That how can you say that the Reynolds stress, and that is the widely accepted view. And but yes, so we have like the order of magnitude calculation so that like the Reynolds stress is still there, but if you compare with these two terms, that is like 4th order of magnitude less. So, but yes, that's true that it is still there.
So would that suggest that both the thermal wind and the meridional flow are acting?
But like, yes, our idea is not that. Like our idea is that the thermal, like that Reynolds stress term cannot like compensate the increase in thermal wind term. So we need the increase in centrifugal term to compensate that effect. But thank you, Dave, to pointing it out.
Great.
Rajaguru, I see you're unmuted. You have another question?
No, thank you.
Anyone else have any questions? Feel free to jump in.
I have a really basic question that hopefully will help me, but also other new to the near surface shear layer people. Why isn't the near surface shear layer purely explained by the combination of convection and magnetic field?
That is, I think, the fundamental question that we all have. But yes, I don't have the answer right now, because in this model also, there's, like you have seen, there is no important magnetic field there, right? So, and we know that it is present there throughout the time. So yes, we don't have answer yet for that, why it is not.
I'm glad I'm getting the
Maybe others
point
can,
of
I'm not
the
I'm very
search.
new to this field, so maybe other can comment on that if they have some answer.
Robert, did you have a comment?
Yes, I just have to comment. So we don't understand convection and we don't really understand the magnetic fields. But apart from this, the convection and the magnetic fields and the rotation will explain in this shear layer with 100% certainty. But unfortunately, we don't understand convection or magnetic fields. But apart from this, perfect.
We're getting there. All right, great. Anybody else?
One thing I would encourage you to look at is these helioseismic measurements, and this is what follows on what Irina was saying, is you're using these cycle averaged helioseismic measurements,
Yes. Yes.
but your technique doesn't depend on that. I mean, you can do
Yes.
it at every instant in time. You can do it every
Yes.
72 days if you want.
Yeah.
So I would beseech you to take a look and see how these results change with time.
Yeah.
Yeah, that will be very interesting, actually. Yeah.
Mhm.
So instead of using, and we can try with the different inversion technique of the helioseismology data as well, because we have the different data now from the GONG as well as from the MDI and SMI. So yeah, that will be interesting, because we have some signature of even the meridional circulation has some cycle dependency. So in the different phase of the cycle, it has different, so that may also have the effect. So yeah, it will be very interesting to look into it. Thank you for the suggestion.
Okay, well, if there's no other questions, then I'd like to ask Riju to close us out with any closing statements that she may have.
Thanks to the speaker Bibhuti again, and thank you for all who attend seminar, and together we have a great discussion. And again, if you know of anyone whose recent work will be very interested to the COFFIES community, please propose a talk either by yourself or by others. So please just contact me, or you can find my email in our yearly seminar announcement emails. Okay, let's thanks to all again, and see you next month.
Thank you, everyone.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
Thank you, Bibhuti.
Thank you.